All right, hi everybody. Welcome to section 1 of chapter 14, where we're going to cover some pretty basic information about acids and bases. First up is going to be the properties of acids, so just some things that we know to be true about acidic solutions. And that is that if you can safely taste it, they tend to be sour. So anytime you've eaten anything sour, think like lemon, that kind of thing. That's an indication that something is acidic as far as the composition of that solution might be. Some of them change the color of acid-base indicators. So acids and bases will both tend to do this. If you're thinking about things like those little pool strips, so those tend to have a range above and below a pH of 7 on the pH scale. And so if it's an acid or a base, it will change acid-base indicators as far as color is concerned. Some of them will will react with metals in order to release hydrogen gas. And in this case, for instance, we have this example of barium and hydrogen sulfate, or sulfuric acid. And in that particular reaction, the barium switches places with the H2 and releases H2 gas as one of the products. Acids are going to react with bases. That's not going to be a property that's going to change for bases either. And in general, when an acid and a base reacts, it produces a salt, so an aqueous salt, like say NaCl, that can dissociate, and then it also produces water, so pure H2O. And the last thing is that acids will conduct electricity. So put an electrical current through them, you can conduct electricity. If you've ever seen the example of like the lemon battery, so you can actually have, a battery made with a current through a lemon. Pretty cool stuff. All right, so just to kind of give you some background on how we name our acids, there's the most common way is a binary acid. So this is going to be an acid that only contains two different elements, so not a polyatomic acid, but one that has maybe hydrogen and then something else. And one of the most electronegative atoms, so something along the lines of a halogen in group 17. Sorry. And of those binary acids, they tend to have a similar way of naming them. So for instance, the first thing is that they start with hydro, because the H is the thing that's in the front, and then the root of the name is going to be the second element that follows the prefix. So for instance, with fluorine, we'd get hydrofluoric. That's the last part of our naming convention for this particular type of acid. We'd get the root of the name of the second element, so fluoride is fluor, and then we'd end it with ic, so hydrofluoric acid. For chlorine, we'd do the same thing, so we'd take chlor, because that's the root of the name of the second element. We'd put hydro in front, so hydrochlor, and then we'd drop the end and add ic, so hydrochloric acid. And all of them, you'd add the word acid at the end. So here are just some of the common binary acids. These are all the names that are involved, but knowing the naming convention, you could name your own. An oxyacid is going to sounds like something that has oxygen in it. A lot of times these are going to be parts of a polyatomic. And what we'll do is we'll kind of modify the polyatomic name to give us the name of the acid. So for HNO3, we know that NO3 is nitrate. So what we're going to do is we're going to take the base of nitrate and say nitre, and then we're going to drop the ending and add IC. So it's going to be nitric acid. With sulfate, we're actually going to get sulfur, right? So we're going to name that first element in sulfate. We're going to get sulfur, and then we're going to drop the ending and we're going to add ic. So sulfuric is what it comes out to be. That pattern kind of carries through to any of the different acids that we can see. So we've seen like acetate becomes acetic acid. Just remember that for the most part, what we're going to do is we're going to drop the ending, add ic and acid, or we're going to drop the ending and add us acid. So for instance, hypochlorous acid, because that hypochlorous acid is different than chloric acid, which is going to be the 8 form of the chlorides. So just kind of name conventions is what we're looking at. So some of the common industrial acids, which are used, of course, in industrial settings to do various different things, are going to be the sulfuric acid, nitric acid, phosphoric acid, hydrochloric acid, and acetic acid. Now, of the 5 that are named here, 3 of these are for sure very strong acids as far as strength is concerned. Sulfuric acid, hydrochloric acid, and nitric acid are very strong acids. A lot of times they're used in different ways. Acetic acid is also known as vinegar for us. It's the main component of vinegar. That acid can be actually strong enough to hurt you if it's a high enough strength, but for us it's typically so weak that it wouldn't bother our stomachs, which is why we can eat it. So just kind of keep in mind that a lot of these have different properties. Your reading goes over a little bit more about what are some of the industrial applications of these different things. Make sure you read that section because that is part of the questions at the end of our lecture today, and what they're commonly used for. For our bases, we're going to get similar properties to our acids. So one of the things that bases have in contrast with acids is going to be that they taste bitter. So if we do eat base solutions, they tend to taste kind of bitter. And we don't, these are the ones you kind of spit out. You're like, gross. Bases change the color of our acid bases indicators, just a different color than an acid would change the same indicator. So if you think about your pool strips, if those of you who have them, maybe you don't, the way that we measure the pH of our water when we're trying to decide if it's okay or not is that we dip a strip into it and it changes color. And those colors range from red down to blue and every color in between. Now, the dilute versions of bases tend to feel slippery on your hands. And so one of the most common bases that you're using is actually soap. And what it does is it actually saponifies the acids on your hand or just the skin cells on your hand, and it keeps like dead cells off and all those lovely things. So that's why your hands feel really soft after you wash them or after you put on lotion sometimes. That's because you're actually putting a base on your skin that's interacting with what we would call, I guess, ecosystem of your skin. I don't remember the technical term for it right now. But yeah, so what it does is it actually makes the environment more basic, and that's why it feels softer. It interacts with molecules in the edges of your skin cells and makes them feel that way. Bases are going to react with acids, and they're going to do the same thing that acids and bases do in our previous section, or in our previous talk on acids alone, and they're going to just produce a salt, so something aqueous, and water, H2O, typically in the liquid form. And the last thing is that they also do produce or conduct electrical current if they are used in the right way. Okay, from there we have our first definition of an acid and a base to discuss, and that's the Arrhenius version of an acid and a base. So this is going to be a compound, so we're going to define types of acids. So the Arrhenius acid is the first type. The second type that we will talk about, and I think that's actually in section 2, is the Bronsted-Lowry definition. It's the more common definition in chemistry, especially in later applications of this stuff. So an Arrhenius acid is one that actually increases the amount of hydrogen ions that are in an aqueous solution, whereas an Arrhenius base is considered a substance that increases the concentration of OH- ions in aqueous solution. Simple definitions. From there, we're going to use them and we're going to apply them. And when we say increases or decreases concentration, we mean when it breaks apart. So here we have an example of a HNO3 molecule that is reacting with water. And the HNO3 molecule is going to break apart into H and NO3. The H ion is going to attach to the water, and it's going to produce H3O+. And in doing so, it increases the H+ on the right side of this equation. So since HNO3 gives away that proton, it's considered the acid because it increases, by adding that proton to water, the H+ concentration on the right side of the equation. So we would call HNO3 the Arrhenius acid in this particular case. From there, we can look at the differences between, say, strong and weak acids, and we'll go into this in depth. But one of the things to know about strong acids is that when they dissociate, so when they hit water, right, like HI, when it hits water, it's going to completely dissociate all of its ions into H+ and I-. Nothing will be left behind. So you'll see that on the left column of this table, the strong acids all go straight to the right. correct? So all of the reactants become products. There is no reversible arrow. But our weak acids are always written with an arrow that points both ways. And the reason for that is that not all of the weak acid is going to dissociate or break apart when it hits water. So some of it will still be in the solution as the original form of the acid, and some of it will also be present as the H3O plus and whatever the other species is. But you'll notice that some of these things have things in common, right? On the strong acids and weak acids, one of the reactants is always water, and one of the products is always H3O plus. That is how acids react when they are in water. All right, so then we can talk a little bit about the strength of acids. So strong acid, like we said, is going to be one that completely dissociates into its two parts. A weak acid is going to be one that kind of lets some of it stick around and not transfer all of it into its products. The big thing here to remember about strong acids versus weak acids is if strong acids completely dissociate, then they are very good at creating the H plus ion. Okay, that's exactly what we want them to do. And if it's a weak acid, it does not completely dissociate, which means it does not produce as much of the H plus ion. So we define strong and weak as how much of the H plus can actually be created when we do this dissociation. With bases, we're actually going to define, according to Arrhenius, how much of the OH is actually created. And with bases, one of the things to note is that when we talk about them, we tend to think of the most common bases as being versions that include the hydroxide ion, so this OH minus ion. In reality, there are bases like NH3 that do not have OH present at the beginning, but that when they react with water, they grab a proton from water and leave behind an OH. So an Arrhenius base is defined as something that creates OH minus, not a base that contains OH minus. Do not get those two mixed up. The strength of bases, similarly, is going to be based on whether or not it completely dissociates. So again, on the left side, we see some strong bases, and all of these examples, all of our strong bases have OH attached to them. All of them, pretty much exclusively. And when that happens, they dissociate into the cation form of the metal and the OH minus, right? So they all have that in common, is that they all produce OH minus. They also all have in common that one directional arrow. So all of the reactants must completely dissociate to become all of the products. With weak bases, we see that double-sided arrow, and we see that when they're added to water, they form OH minus. You'll also see that most of our weak bases do not contain OH to begin with, okay? So just remember, the acid is defined by its ability to create OH minus. It is not defined by the fact that it has OH minus in it. Just to kind of give you an idea of an acidic versus a basic solution, we have this kind of summary table in your chapter, which describes to you how the concentration of H3O plus compares to OH minus. I highly recommend you take a look at this. It tells you that if you have a certain concentration of H3O plus at 10 to the negative 7 molar equal to the same thing with OH, then you're actually in that neutral solution. And we'll kind of, we won't look too much into pHs beyond this is kind of what it is, but just understand that when we talk about acidic versus basic, when we say something is acidic, it means it has more of the H3O plus than it has of the OH minus. When we say it's basic, we mean it has more OH minus floating around than it does H3O plus. All right, that brings us to your questions for this lecture. You may use your book, you may use this lecture to go back and define the differences between strong and weak. Make sure you define the Arrhenius base and acid. And then I want you to do the research and figure out what are the properties of some of those acids that we talked about that have industrial usage. And then I also want you to state 2 properties of aqueous acids and bases. Please do not state the same one twice. So look for the ones that distinguish an acid from a base. That is all. Have a great day.